Good day. We've just gone over a sheet looking at the different functional groups, and it takes practice. It'll take a while to be good at this stuff. You have to get good at recognizing what functional group you're dealing with, because if you don't identify it correctly, you're not going to be able to name it properly or draw its structure properly. And once you can identify them, and that should be, it shouldn't take long to learn that. The naming is the harder thing, and the drawing structures are actually fairly easy. So you've watched the previous videos on how we deal with all these functional groups, and you've seen examples. And so now we're going to test this out and see how you do. Well, the heading tells us it's an alcohol, and we know it's an alcohol because we have an OH. The find the longest sausage stuff still applies. We would like to call this ethane. So we go ethane. So we say, why would it be ethane? Well, we have two carbons. So we go ethane. And then what we do is we say, you know what? We got to fix the ending. Alcohol is named by the OL. So we go bye-bye E and put the OL. And now we're going to have the perfect name. And there's a dog drinking. Fairly unimpressed. He's not drinking alcohol as far as I know. All right, so that is ethanol. I didn't have to put the location of the alcohol, the OH, because it had to be on one of the end carbons. Both carbons, one or the other, if I stuck on the other one, I'd still have the same thing. So that's why I do not need the location. Again, you see we're onto another alcohol, but this time I have three carbons in a row. So it would be propane, and it becomes propanol. But this time I have to put a location, because it could have been on one of these end carbons, here or here, or it could be on the middle carbon. Since it's on the end carbon, it becomes 1-propanol, and then we stick in a hockey rink. Beautiful, so professional. Next beast. No, that's going to tell you why you had to put a location. Had to put a location in because we have to give that information for someone who is trying to draw a structure. They have to know, where does the OH go? In this case, it goes on the end. Apparently, we have another alcohol. And a close cousin of the last one. Again, we have propane, but this time the OH is on the second one, so it is 2-propanol. Alrighty. State location, blah, blah, blah. Another alcohol, my goodness. Well, we got to find the longest sausage, so we do that. And then we have the OH, which we'll deal with, and we have the bromine, which we'll deal with. And when we count, we're probably going to count from the left to get our lowest addresses, to get that 4 over there and the 3 for the bromine. So we get 3,4-heptanol. The 3-bromo tells us the bromine's on the 3rd carbon, and the 4 tells us the alcohol is on the 4th carbon. Now we're looking at ethers. Oxygen, and it has a carbon chain going out this way and a carbon chain going out this way. Now there are a couple of ways of naming ethers. Sadly, we do the trickier way. A lot of people would like to go and say, you know what, this looks like butyl-propyl ether. And that is one way. But we're going to include the oxygen as part of a branch. Boy, that's a mess. Let's just tidy that up. Okay, so let's say that this is our main chain here, and this is going to be our branch. So our main chain is butane, and then this is going to be propane, and has an oxygen, so it becomes propoxy. And we go 1-propoxybutane. And the dog is trying to eat my glasses. How helpful. Very strange. So we get 1-propoxybutane. So we can see it's coming off an end carbon there. And the shorter branch was treated as the oxy, and the main chain is treated, so an ether is treated like as an alkane. But technically, if you called this butyl-propyl ether, it would be marked right as well. A lot of times people find that easier. Now the carbonyl group is one we're going to run into a bit. And it's going to have a trigonal planar structure, 2 bonds here for the carbon and double bond to an oxygen. And we find it in things like aldehydes and ketones, and we sort of find it in carboxylic acids and esters. There's a slightly different name for them. Aldehydes, this functional group is always at the end of the chain. And this carbon is always given carbon 1, and you count there, and there's 1, 2, 3, and you go that way. And we see we have a branch there, and we go 1, 2, 3, 4, 5, 6. So we know we're going to have a 6-chloro. Our ending, our suffix, is going to be al. So how many carbons do we have here? 1, 2, 3, 4, 5, 6, 7. So we know this is going to be a heptanal, and then we stick the chloro on. So it becomes 6-chloroheptanal. The trick is to count from this end. We love it. It tells us which end to count from. Always, always, always. And when we get to carboxylic acid, same thing. So, here's the simplest aldehyde, a nasty aldehyde. That's just methanol. There's just 1 carbon there. And the old name was formaldehyde. Wait, a gentleman. I guess Dr. Heinrichs, he had a PhD, and he wisely hated formaldehyde. Nasty, nasty preservative. Ketones. Ketones have a carbonyl group, but they're not allowed to be at the end of a chain. So it's like an aldehyde, but not at the end of a chain, somewhere in the middle. Well, it can't be on this carbon, can't be on this carbon, that group. It's on one of the 2 middle ones. This is going to be butanone. We don't have to put a location because we know it can't be on the end carbon, and these 2 interior carbons are equivalent. So 4 carbons is butane, and then the ending is replaced. We get rid of the E and add not 1, we add one, butanone. Very musical. Alrighty. So you've seen that in the previous notes. Another ketone. Well, we got to find our longest sausage. Boom. And we want to give it its lowest address, so we're going to count from this direction. In this case, we have to give a location. So it is on the 2nd carbon, counting from the right. And so it is 2-octanone. We definitely don't want to count from the left and may hit 7-octanone. That would not be clever. Carboxylic acid cleverly has a carboxyl group. It looks like oxygens are bonded together, but they are not. This carbon, that oxygen is actually double bonded to a carbon. This is how they like to write it out. And this is ethanoic acid, known as the active ingredient in vinegar. And the old name was acetic acid, based on the acetate ion. Modern name is ethanoic acid, because we had 2 carbons our longest chain. So whenever you see COOH, it's a carboxylic acid, and it always occurs at the end of a chain. So here it is. It's occurring at the end of a chain. There's our COOH, and it's included in our longest sausage. And then we have our branches. And boy, that's easy to read. So we end up with a 3,5-dimethyl, because we had 2 methyls. Hexanoic acid, 1, 2, 3, 4, 5, 6 carbons. Again, if you're systematic, this will get easier and easier. And automatically, this is carbon 1. Esters I'm going to do in the next PowerPoint, because I think students tend to find esters difficult.